turns out to be that one, such that if you concatenate these braids and pull, what's going to happen if you pull? Well, look at the bottom strand here. That's certainly just going to slide out. That disentangles the second strand, and then you look at the diagram for another second and see that the first two disentangle as well. So if you pull, you get the trivial configuration back. So we've seen that this braid has an inverse with respect to this multiplication, and that's true for every braid. So the existence of inverses is one convenient property. There's two more. And the collection of these convenient properties is what algebraists mean when they say that braids form a group. So braid multiplication, if you're not an algebraist, has one property which you'll find a bit peculiar. It is non-commutative. What that means is that the order of factors matters. And if you're looking at pictures, it's pretty obvious that this is. So if you look at these two braids and multiply them, well, you multiply the left braid by the right one, but one's from the right and one's from the left, you get these two pictures, and if you look at this for half a second, you see that they're not the same. So for braids, A times B is in general not the same as B times A. Apart from that, braid groups have a very rich structure. This structure can be described at a more abstract level, and this is where the algebraist gets happy eyes. We can abstract again and define something more generalizable. If you do this, keywords that you would use are partial orderings, greatest common divisors, least common multiples, lattices in the combinatorial sense, and all of these words really come from combinatorics. So this is where where combinatorics comes into Garside theory. Garside groups are simply more general groups which you can define using these combinatorial terms, so they generalize the abstract structure that Garside groups have. So if you look at the definition, a combinatorial lattice plays a key role there. In some ways, Garside groups behave like braid groups, but they are more general and hence have a few less properties, and the question is to make that precise. I said algebra, combinatorics, and computing. This is where computing comes in. I'm especially interested in algorithms for Garside groups, that is for methods for computing in these groups in practice. One question on which I spent a fair bit of work is methods for solving the equation x inverse times a times x is equal to b for the variable x, given braids a and b, for example. Being able to do that, being able to compute in these groups, is useful for two reasons, and John mentioned one of them in his talk. I'll start with the other one. The first reason is the obvious one. If you have applications that involve braids, more likely than not, you will have to do explicit computations, so these algorithms will be used. The second, for me, more interesting reason is because being able to perform computations in these groups in practice allows me to perform experiments, to look at large examples, to try to recognize patterns, and thus to investigate the structure of these groups and hopefully get ideas for how to prove and publish theorems. This is where computing comes in, and as a matter of fact, designing efficient algorithms and data structures, and also a fair bit of programming, are quite important aspects of the mathematical work that I do. Now, why? Well, to be honest, the main reason for me is because I think that this is nice mathematics. And remember Dirac, of course, there was a reason why I put that quote in. However, we don't have to, unlike in the case of number theory, we don't have to fast forward 40 or 50 years in order to see practical applications. There are already now applications in mathematics and physics where braids play a role. Just to drop a few names here, in mathematics you've got knot theory, you've got low-dimensional topology, you've got operator algebras, and you've got Lie theory. In physics you've got quantum statistics, scattering theory, quantum field theory, and string theory, just to name a few. Another application which I'm interested in is applications in cryptography, that is data security, encryption schemes. And in that regard, it is exactly the non-commutativity of break groups which makes them interesting. Most established cryptographic schemes work with commutative groups like point groups of elliptic curves or modular integers, and they all have one thread currently hanging over their heads, and that is quantum computing. Because the structure of break groups is substantially different, it is quite unlikely that braid-based crypto schemes are vulnerable to quantum computing, so that's certainly a reason for investigating them. To finish off, I want to mention some of my collaborators. I've had the fortune to work with a lot of very nice and very good people in the last couple of years. Most of them are from Europe, but in alphabetical order, the first two aren't. So I've worked with John Berwick from Singapore, John Cannon, who's leader of the Magma Computational Algebra Group at Sydney Uni, Patrick Doranois and Eddie Godel from France, Juan González Meneses from Spain, and Luis Paris from France again. If you want to read on a little bit more, this is what you could look at. These are papers that arose from this project since last year. And the project has also got in a bit of money. Unfortunately, there's no lines for 2014, but I'm working on that. I did work on that this February, so I hope to be adding another point.